This short video is a brief introduction to the Millsian molecular modeling software. Millsian is the software for the prediction of structures, energetics, electron distribution, and physiochemical properties of molecules based on classical physics, electronic structure theory. Traditionally, quantum mechanics has been employed to calculate the electronic structure of atoms and molecules using Schrödinger equation. Let's take a look at the performance of a quantum mechanical method. This plot shows the predicted total bound energy for a series of molecules in the y-axis versus the experimental data in the x-axis. One would expect the data points lie on the diagonal for a perfect method. However, most of the points on this plot show significant deviation from the diagonal. For example, the experimental value for the tetrachloride carbon is 13.4483 electron volts, but the calculated value is 207 electron volts. The explanations standard deviation. The hydrophobicity 631G method does not accurately capture the behavior of electrons in this molecule. For comparison, let's calculate the total bound energy for the same molecule in Millsian. One of the easiest ways to generate the molecules in Millsian is to use a SMILES representation of the molecules. It takes less than 1 second to finish the calculation for tetrachloride carbon. The calculated properties are displayed in the Millsian property window. This calculated value is 13.4318 electron volts, which is in excellent agreement with the experimental value of 13.4483. This excellent performance of Millsian is due to the fact that classical physics accurately models the electrons in the molecule. The color scale on chemical bonds shows the electron density. As expected, the electron density on the oxygen atom end is larger than the hydrogen atom end in methanol due to the higher electron activity of the oxygen atom. The calculated dipole moment for methanol is 1.71 dBi, in good agreement with the experimental value of 1.69 dBi. This plot summarizes the overall performance of Millsian for the same set of molecules used in the hydrophobicity calculations. As expected, all the data points lie on the diagonal. The average absolute error is only about 0.1%. Other properties, such as 3D structures, are extensively used in drug discovery. Millsian implements a robust toolset to calculate the 3D structures from 2D representation of molecules. One of the challenges in 3D structure generation is the constraints imposed by complicated rings. In this demo, we input the SMILES for a small series of fused and bridged rings. Millsian generates the structure and calculates the properties for this complicated molecule almost instantly. Another feature to note is that Millsian correctly reproduces the chirality of atoms in a complicated molecule. Based on classical physics principles, Millsian is able to calculate the charge distribution and energetics for large biomolecules such as protein and the DNA strand. This is remotely feasible for quantum mechanical methods. To demonstrate this feature, we read in a PDB file of protein called human dihydrofolate reductase. It takes about 1 minute to calculate the charge distribution and properties of this large molecule with more than 3,000 atoms. Users can rotate and zoom the molecule to examine its structure. The protein chain and substrate can be visualized separately in Millsian. Millsian can help medicinal chemists to analyze the binding between ligands and protein by examining the charge distribution and the structure of the ligand and the active site of the protein. The results for structures, energetics, and the charge distribution are encouraging. Currently, Millsian is being extended to predict the hydrophobicity of molecules, usually represented by log P. Based on the same way that bound energies and electron distributions are calculated, the log P properties of molecules are calculated from the bound and atom contributions. This final plot shows the log P value predicted by Millsian and measured in experiments. About 780 molecules from the log P star list are selected for the test. The average prediction error is around 0 with a standard deviation of 0.19 log P unit. For comparison, 0.4 to more than 1.3 log p units of error have been reported in literature.